Hello and welcome. Today we want to learn about the inner product space. So we are using an example and it's a question. It says that verify that the following is an inner product on the 2 space. And the inner product is defined as UV is equals to U1 V1 minus U1 V2 minus U2 V1 plus 3 U2 V2. So the term verify means that you have to cross-check that this here is an inner product, meaning the axioms of inner product space are being tested. But now here, since it's a 2 space, U is equals to U1 U2, V is equals to V1 V2. And now we start with the basic. So the first thing you're going to prove is UV. The inner product of UV is the same as the inner product of VU. So this is quite simple because our definition is that UV is equals to, so we have U1 V1 minus U1 V2 minus U2 V1 plus 3 U2 V2. So we start with V1. We're just using the definition, minus V2 U1 minus V1 U2 plus 3 V2 U2, which by definition becomes VU. So we have axiom number 2. So, or maybe I write the axiom for you here. So our first axiom is that UV is VU. Our second axiom is that U plus VW is the same as UW plus VW. And then our next, we have lambda. And now we have a fourth one. It's greater or equals to 0. And it's only 0 if all the components are 0. So our axiom 1 here is checked. So next we're going to axiom 2. That means you're going to define an extra lambda, not lambda really, but W. So you're saying W is equals to W1 W2. So we have U plus V will be U1, this is vector addition, U2 plus V2. Now we want to put the 3 together. So you're going to have U plus V W is going to be U1 plus V1 U2 plus V2 and then W1 W2. But keep in mind our inner product space is defined. We have it here. So we have, we're going to use U1 plus V1 into W1 minus, so somebody will ask what determines whether you're using u1 or you're using u2 plus v2. You check here. So we have u, it becomes u plus, this one is u1, it becomes u1, this one is u2, so in that manner. So here we have u1 plus v1, but now here this is v2, so we are saying w2 minus, this is u2, it's going to be u2 plus v2, this is v1, so you're putting here w1 plus u2 plus v2 w2. Now we collect the like terms, not really collecting, but we are expanding. But here we are forgetting a 3, we have a 3 here. So we have u1 v1 u1 w1, sorry about that, so this one is going away. So u1 w1 plus v1, we are expanding, plus v1 w1 minus u1 w2 minus v1 w2 minus u2 w1 minus v2 w1 plus 3u2 w2 plus 3v2 w2. So we have to collect all the u's and all the v's. So we have u1 w1 minus u1 w2 minus u2 w1 plus 3 u2 w2 plus v1 w1 minus v1 w2 minus v2 w1 plus 3 v2 w2. So from our definition, this first bracket is uw and this second bracket is vw. So our second axiom here is satisfied. Now we're going to our third axiom, which is pretty obvious. So our axiom 3, we're going to write it here, is that lambda uv is equals to lambda. So what happens is we multiply lambda u, but our u is u1 u2, which becomes lambda u1 lambda u2. So if you are taking lambda uv, you have lambda u1 lambda u2, then you multiply v1 v2. So remember, our uv is defined, so you're multiplying lambda with each item. Lambda u1 v2 minus lambda u2 v1. So you can just cross check back for the equation so that you don't make errors. So we are writing this clearly. So you have plus 3 lambda u2 v2. So we have lambda, which is common all across, so we are factorizing out our lambda. We have u1 v1 minus u1 v2 minus u2 v1 plus 3 u2, v2. But now from our definition of this here is, so we are getting lambda into uv. So our axiom 3 is satisfied. And now on to our last axiom. Our last axiom states that u of u is greater than 0 and will only be 0 if the components are 0. So what we are going to do is first take this inner product and see. So this is just the inner product of u by itself. So we are multiplying with u1, u2. So that is the inner product of that vector by itself. So but we have a definition. So in our definition, wherever we have a v, we are replacing it with u. We are going to get u1 squared. We can always pause and go back and confirm our definition. u2, u1 plus 3 u2 squared. So this is u1 squared. This are the same thing, u1 u2 plus 3 u2 squared, but this one can always be expanded. So you will get u1 squared minus 2u1 u2 plus u squared, and then you're putting plus 2 u2 squared. Automatically there's no way that this can be 0. So this part here in bracket is u1 minus u2 squared plus 2 u2 squared. But this one is, there's no way it's going to be 0. So we are saying, and that inner product will only be 0 if and only if both u1 is 0 and u2 is 0. Because if u1 is 0 and u2 is not 0, then still you're not going to get 0. So this has proved that. So we are saying that thus our inner product uv, this one is an inner product in the 2 space. Thank you. Kindly join us on the next as we continue to explore more topics in linear algebra. Bye.